In this video, we're going to walk through the math in Appendix 6A of Just, Hueth, and Schmitz. They start with the definition of the expenditure function, which is simply the solution to a minimization problem where we're choosing the vector of choices Q to minimize price times that Q, where both P and Q are vectors, notated by the bold in their font, subject to the constraint that the utility at that level of choices Q is equal to some baseline level, let's say Q bar, and they have a non-negativity constraint on Q, all of the elements of Q. If the utility level U bar was associated with the income level M, then the expenditure function evaluated at U bar is simply equal to M, which is also equal to price times the Hicksian demand, notated with the upper bar on the Q function there, times price times the Hicksian demand at U bar. And the indirect utility function is simply the inverse of the expenditure function. Again, in this case, we're recovering U bar, that is, the indirect utility function is equal to U bar at the original income level M. Noting that the indirect utility function at P0, M0 is equal to utility level U0, and at P1, M1 is equal to utility level 1, how do we measure the difference between U0 and U1? Well, we can do that with either compensating variation C, where we simply subtract from M1 the level of C, which is also measured in monetary units, or we can add, in this case, E to M0 on the right-hand side. Both of those are legitimate measures of the change in welfare associated with moving from P0 to P1. We can also write C and E in terms of the expenditure function by noting that the indirect utility function evaluated here at P1 M1 minus C is equal to, by definition, V of P0 M0, which is also equal to the U0. So if we invert the indirect utility function to obtain the expenditure function, you obtain M1 minus C1, which is equal to expenditure function evaluated P1 U0, which is also equal to the inverse of P1 U0. And then simply simplifying, you obtain that C is equal to M1 minus the expenditure function P1 at U0. And similarly, we can do the same thing for the equivalent variation metric as E of P0 U1 minus M0. Note that the Hicksian demand function is simply equal to, or the expenditure function can be written in terms of the Hicksian demand function as shown here, and we could take the derivative of the expenditure function with respect to the vector P, and then using the product rule you obtain the Hicksian demand function Q bar plus P times the derivative of Q bar with respect to P. But we can look at that second part of that derivative and find that the derivative of Q bar with respect to P is simply equal to 1 over lambda dq dq, where du dq is equal to the derivative of the utility function in the standard utility optimization problem. Lambda is the shadow price on the budget constraint. And then, but we know that du dp is equal to 0 since U bar is fixed. Hence, the second part of the expression drops out, and we're left with the result that the derivative of the expenditure function with respect to price is simply equal to the Hicksian demand. Hence, we can obtain the difference between the expenditure evaluated at P0 and the expenditure function at valued at P1 by simply looking at the areas underneath the Hicksian demand functions, that is, over that whole vector. Now you'll notice that we're integrating over from P0 to P1, but both of those are vectors. We're going to talk about how we do that integration under many price changes down below. We said above that C, compensating variant, is simply equal to M1 minus expenditure function at P0 U0. Well, so let's add into the middle of that. We're just going to add 0 by adding or subtracting M0 and then adding expenditure at P0, U0, and the sum of those two terms is equal to 0, so we haven't done anything. But now we've got it written in a way that is easier to handle, and that is that C, compensating variation, is equal to the change in income, that is M1 minus M0, plus the change in the expenditure function, which, as we've shown above, can be found by integrating underneath the Hicksian demand functions. And as I said above, the line integral, that is the integral over a bunch of prices, is obtained as follows. First, you integrate under the first element, holding all of the other elements of the price vector at the original values P20, P30, etc. And then you move on to the next piece. That is, we now holding P1 at the new value, P11, and we integrate under P2, holding the remaining values at 0 at P30, P40, etc. And then we move to the next one and the next one and so on. And in this way you can integrate under as many changes in the price vector as we need to. You simply need to do it in the right piecemeal fashion. And just as with compensating variation, equivalent variation can be derived in the same way. We add 0 in here, and then we see that we can express the equivalent variation as a difference in the expenditure function plus a difference in income, which leads us to that expression right there, which is the line integral under the Hicksian demand functions plus the change in income. And as we did above, we can use a sum notation. In this case, I'm writing it a little bit more succinctly, where we're simply piecemeal, one at a time, integrating under each of those Hicksian demand functions, moving across the prices from 0 to 1 to 2, etc., as each of the for each of the prices that change. We can now use 6.29 and 6.30 to figure out what's the difference between equivalent variation and compensating variation. The difference is going to be the difference between those line integrals, expressed here as the integral from the vector P0 to P1 of the Hicksian demand function evaluated at U0. That's the compensating variation part, minus the Hicksian demand function P for U1 for the equivalent variation part. And writing this in sum notation, we get to the point where we can think about these as little pieces where we're varying one price at a time for both the utility level U0 and the changed utility level U1. That is the compensating variation part and the equivalent variation part.
So an interesting question is, when is compensating and equivalent variation going to be equal? Well, we can take those two expressions for compensating and equivalent variation and we can write them like this, where we have the compensating variation measure of surplus using the Hicksian demand curve given U0 minus the equivalent variation part where it's equal to using U1. And we can notice that we can write that as a double integral where we're now integrating not just over price but also over the utility levels. So we can then move down here to say, well, let's look at that middle piece of that integral and notice that Hicksian demand and Marshallian demand are equal at the initial income level M. Taking the derivative of that with respect to M, you get dQdM is equal to the derivative of the Hicksian demand curve, which can be written out using the product rule as the derivative of the Hicksian demand with respect to utility times the derivative of the indirect utility function with respect to M. Now, of course, the derivative of the indirect utility with respect to M is certainly positive, so we can divide through by that, and we end up with this expression here that dQdM divided by dVdM is equal to the derivative of the Hicksian demand curve with respect to U. When is that going to be equal to 0? Well, it can only be equal to 0 if dQdM is equal to 0. Hence, we are left with the curious result that Hicksian demand curve, the equivalent and compensating variation measures are going to be equal only if the derivative of the Hicksian demand curve with respect to income is equal to 0. That is, we're only Hicksian and or the equivalent and compensating variation are equal if and only if there is no income effect. So the income effect, if that equals 0, that is, if you give somebody a little bit more income, they don't change their consumption of that particular good, then in that case and in that case only will compensating and equivalent variation be equal. We're going to explore this a little bit more and see how big of an error there is between the compensating and equivalent variation, how much difference there is, which will then tie into how big the gap is between compensating and equivalent variation in the next part using the Willig approximation.